Hey guys, thanks for tuning in and watching my video. I know who Mike. I know you gotta watch this. So anyway, for this lab, we have a swing massing from a we have a mass swinging from a spring, and our task is to model the path of this mass as it swings and compare it to the observations that we see in the video. We're also going to be graphing the changes in kinetic, spring potential, and gravitational potential energy. And for our results, well, we'll be seeing those later on in the video. For the creation of our model, we're going to be using two main fundamental principles, those being Newton's second law and the energy principle, which states that the change in energy is equal to the sum of the changes in kinetic, gravitational potential, and spring potential energy. So we know going into this problem that our spring and mass system are not going to be absorbing or releasing any energy into the surroundings. So we can expect that there's not going to be any change in energy. We also know that the mass hanging from the spring is 0.402 kilograms, and that the spring constant K of the spring that it's hanging from is 6.83 newtons per meter. And we can also extract the length, the relaxed length of the spring, and the initial position of the mass using the tracker video and the last video from an earlier lecture. Alright, now we want to go take a look at our video in tracker. So here's tracker. And we'll run through the video one time, even though I know you must have seen it at least a few dozen times by now. Anyway, so this is the path of our mass swinging on the spring. And if we move back over, we can see that the data table for the position relative to time with respect to time is here in this table here, but continues to extend on beyond the page. And that data is going to be exported into a CSV file, and we'll see that later on in the code. And the relative position of the mass with respect to the x-axis with this graph on top and the y-axis with this graph on the bottom shows the position of the mass. And by using the nodes here and computing the average time interval over 3 periods, we can derive the different lengths of time of a period on the x-axis and the y-axis, and those values are seen here. Okay, now that we've seen what our observations are going to look like in real life and we've gathered our data points there, it's time to create our model. So we're going to initiate our model by filling in these conditions. We know the mass of our object being 0.402 kilograms. We know the initial position given to us from tracker and also stated on earlier in the video. And we saw that in the video the mass was released from rest, so velocity is 0. And here, these lines of code are detailing how the CSV file that we saved our data into is going to be read. And furthermore, we need to also initialize a couple extra data points for our model, that being the constant of gravity, the K value of our string, the relaxed length of our string, and these lines are detailing, calculating the length of the string for later on in the calculations. And we can see here, if we breeze right on through this, these lines of code are used to detail our initial energies, being kinetic, gravitational, and spring. And these lines are Newton's second law, giving us the position of our mass over time. And these lines, furthermore, are again calculating the initial energies with each respective iteration of the calculation loop. You can also see that our kinetic energy, gravitational energy, and spring energy are defined by our identities that we also know as kinetic energy being mass velocity squared, and so on and so forth. Alright, and one last thing before we go ahead and run our code. We're going to be graphing the code, and we're going to be putting 4 plots on this graph. And we're going to be graphing delta K, change in spring potential, gravity potential, and delta E with respect to time. And just, we have them color-coded. Our graph of E is going to be yellow, graph of K is going to be the blue line, graph of gravitational potential energy will be green, and graph of spring potential will be red. So let's go ahead and give our model a run and see what happens. So we'll see that we've got the graphs here. This graph on the right is growing, and we see the red, blue, green, and yellow lines with respect to time. The blue line here is the track of our mass based on our computer model. And worthy of note is that the red line, or the red ball, is the actual observed position of the mass in the video, and it's really jumpy because the video records in frames and very specific time intervals, whereas our blue ball is generated on a much smaller interval, so it's a much more smooth path compared to the red one. but you can see that they've very roughly followed the same path. So now that we're done with everything, we want to know whether or not our energy principle is satisfied. Well, if we look at our graph, we know that our yellow line represents E, and if we want to consider the energy principle, to reiterate is here on the page one more time, we know, when going into it, that no energy was entering or leaving the system, so there shouldn't have been a change in energy, and our graph confirms that idea. So E is 0, which we expected it to be going into it, so yes, our energy principle is satisfied.